Okay, so welcome in this video we're going to look at the properties of exponentials. Okay, not all of them, but some of the properties here. And in this theorem it says if P and Q are any real numbers and R is a rational number, then these properties hold. Okay, so what are those properties? That if we take in the product of two exponentials, that we add their exponents. Okay, if we're taking the quotient of two exponentials, two natural exponentials, then we're going to subtract the exponents, top minus the bottom. And then here we have a power raised to a power, and so the property here is that we multiply the exponents if we have a power raised to another power. Now, algebraically, these are easy to solve. Okay, but let's prove the first one. I'm not going to prove all of it, but let's prove the first one. Now, it's obvious that if P and Q are rational numbers, that this works by the definition. Okay, because if they're rational numbers, okay, let's just do the first one. By the definition, we can use the property. So if R is a rational number, then E to the P and E to the Q, it's obvious that if we take the natural log of E to the P, E to the Q, right? Well, this equals the natural log of E to the P plus the natural log of E to the Q, which is then going to equal P to the natural log times the natural log of E plus Q times the natural log of E. Now watch. Now I can factor out the natural log of E. So this is going to become P plus Q times the natural log of E, which then becomes, voila, the natural log of E to the P plus Q. Okay, so now, it's obvious that if they're rational, we can apply the properties, because by the definition, right, that we saw earlier. Okay, but what if they're irrational? Well, if they're irrational, then we have to use the definition that we're going to use the inverse function. And so we use the inverse function here, the inverse function definition, to find the answer. Okay, so we take the natural log of this product, right? And then we go through the properties of logs and we get to here. Now, this is where we're going to use the fact that the natural log function is a one-to-one function. And since it is a one-to-one function, we know that if these are equal, right, if the logs are equal, then the arguments must also be equal. Okay? Because it's 1 to 1, then we know that the inverse exists. And so if this is equal to this, then we know that this must be equal to this. And so there's the proof for the first one. I'll leave the other ones for you to prove. Have a great day.